Alright, so the Dead Sea is the saltiest and deepest hypersaline lake in the world. Hypersaline meaning above the normal salinity, like compared to the Mediterranean Sea or the Red Sea right next to it. Um, in the Dead Sea, there's a few different ions. There's magnesium, chloride, sodium, sulfate, along with a few others. But my task was to identify the salt that was most likely to precipitate in the Dead Sea. Right off the bat, I noticed that chloride had exceptionally high concentration in grams per liter at least, which turned out to be true for the molar concentration as well. As you can see here from my calculations of the Q values, this is not the KSP because it's the current concentration rather than the maximum, which is what the KSP would be. The ion product of sodium chloride was equal to 11 with a high concentration of chlorine. And the chloride ion actually turned out to be at a 6.3 molarity, which I thought was pretty wild. In this little KSP expression, I just multiplied the concentration of sodium with the concentration of chloride, and I got this 11 mole squared. Magnesium chloride was the next salt that I was trying to discern whether it would precipitate or not, using a similar process, but this time, because magnesium is in group 2, it needs 2 anions for each cation. The magnesium equation was similar, still used the chloride, but it was a 1.8, and the chloride term was squared, yielding a much higher Q value of 72.26. Magnesium sulfate was the final one. To find this, I had to do some real thinking, because sulfate was not listed on the table as a concentration. Instead, I had to cue into the fact that the Dead Sea is electronically neutral. That means that the concentration of positive and negative ions in the Dead Sea are in an equilibrium, so they make a neutral charge. For this, I took the molar concentrations of all the ions in the Dead Sea, their charges, multiplied those two together to get the molar charge. After adding that all up, I found that it was still positive, which meant there was room for the negative sulfate ion. The negative sulfate ion has a charge of 2 negative, so I divided my positive charge remaining by 2, because I realized that for each mole of sulfate, it would subtract 2 molar charges. So I divided the molar charge by 2, and that was it. That was the concentration of the sulfate as a molarity. I then multiplied that by the magnesium to get the ion product, or the Q value. I then had to compare the Q to the KSP to determine how close each compound was to precipitating. In sodium chloride, I got a KSP value of 37.32. I looked this up because I was a little bit uncertain, but I found that my value was acceptably close, within like 10. Q was smaller than KSP, excuse me. Magnesium chloride, I did a similar process. In this table, though, that I got the accepted values from, the solubilities from, to calculate the KSP, it was in grams per 100 milliliters. So grams over 0.1 liters. So I had to multiply these by 10 in order to get a actual molarity value. An actual grams per liter. Dividing the grams per liter value by an atomic mass immediately yields the molar concentration. And then I just had to take into account the molar ratios and multiply concentrations of ions together. to get the accepted KSP value. My process for the final one was the same, using my value of sulfate that I calculated. For all these, the KSPs were much greater than the Q, but say for magnesium chloride, it was only 10% as concentrated. So the Q value was, I said magnesium chloride, the Q value was 72.3, and this was 739. So, like, a pretty close approximation of 10% as concentrated. It was pretty similar for magnesium sulfate, except it was 0.04, I think, and then 4.66, so another 10%. The only one that was an outlier was sodium chloride, and the Q value I found for the ion product value I found for sodium chloride was an 11. And then the KSP was the 37 that I mentioned earlier. And that was about a third of the way as concentrated, so, or 30% about as concentrated. Which means that no precipitate will immediately form because none of the Q values equaled the KSP or were greater than the KSP. But sodium chloride would be the first precipitate to form, especially if sodium was added as I noted earlier, chloride was in a surplus. I just looked at this, does your answer make sense? Found that my answers did make sense. The charge difference, so the question was, compare your KSP expressions for sodium chloride and magnesium chloride. I explained this a little bit, the charge difference and the difference in the KSP, or the ion product equation. Just the anion term would be squared because for each cation, there'd be 2 anions compared to the sodium chloride. Which of the 3 salts is the least soluble? That actually came from the table, just in the grams per 0.1 liter. And I found it to be consistent with my KSP values. So a lower KSP value is less soluble. And that was consistent. For the got it, I just did these extra problems. Sodium chloride precipitates at the lower depths of Dead Sea. What are the concentrations in grams per liter of sodium and chloride needed for precipitation of NaCl at these depths? Taking the accepted KSP value, I simply split it into the concentrations and then multiply them together. Well, just to get the KSP value again. To double check my work. But that led me to a 6.11 molar concentration of each ion, the sodium and the chloride. The chloride was already at a 6.3, so just an increase of 0.4, I think, molarity. Or, I mean, 4 molar solution would be enough to precipitate the ion. In grams per liter, that'd be 140.47 grams per liter of sodium and 216.6 grams per liter of chloride. The chloride was already there, sodium needed to be added to precipitate. The question about the Yucca Mountain repository gave me 2 concentrations. I simply had to multiply them together in order to get the KSP value. Thank you.